Hi, Frazier Solo here again. Today we are talking Lab 9, calorimetry, counting calories. Alright, so let's see, get into the slideshow here. Pointer options, pick up my pen. So what are we doing in this lab? All right, number one, about your learning, you need to spend the time to read this stuff, study this stuff. It doesn't read like a novel. It requires careful reading, highlighting, rereading, that kind of thing. That's growing your mind, and that's your education. You might not remember this stuff. That's okay. Nobody does, unless you stay with chemistry and do these kinds of things. But that growth in the mental capacity is what stays with you. So we'll determine the specific heat capacity of water. You probably have heard of 4.18 joules per gram per degree centigrade. That's the specific heat capacity of water, and it happens to be a high number. You don't know it's high until you've compared it to other things. So for example, if you look at aluminum, it is 0.9 joules per gram per degree centigrade. So water is so much higher. Well, how about ice? The enthalpy of fusion, that is the amount of energy required to melt the ice. Now, when we're dealing with ice, we're at a fixed temperature, phase changes are isothermal, so the unit is joules per gram. So it happens to be something like 33 joules per gram for the amount of energy required to melt ice. So those are the things we're determining. So a little thermodynamics here. You probably have seen this equation. Yes, you have. You define something as a system, and then it has its surrounding. If you define Q as the heat absorbed, then within the total system, then something absorbs, something gives up heat, and something loses heat. Having defined Q as heat absorbed, then you end up Q system is equal to minus Q surrounding, and you end up with this equation here. Turns out that this is the fundamental equation that says energy is not lost, it's only transferred from one place to another. All right, so we want to be able to calculate the energy. So if you have a certain mass and it's absorbing energy, it'll go up in temperature by a certain degree. Then the heat absorbed, as you're sure you've learned in class. Let's see, my pen is not working. There it is. Q is equal to M. Q is equal to M, where M is the mass, delta T, and the C. The C is the proportionality constant, and that would be the specific heat capacity. Delta T is TF minus TI, final minus initial. And then if you're not changing the temperature and you're just doing a phase change, just like boiling water, then the heat absorbed is just used up in converting the physical state. So Q is equal to M times delta H, where delta H is the enthalpy of fusion or of boiling or whatever it may be. So joules per gram, C has units there of joules per gram per degree centigrade. All right, moving right on. Now the question is, in our case, when we want to determine the specific heat capacity of water, what do we do? Well, number of ways of doing this, but we will take the more proficient, kind of elaborate, advanced one, and that is we're going to use heat energy. So we're going to supply the heat to the water electrically, and then we're going to use some power source. So it will be some voltage, in this case DC volts, and we'll process it for a certain amount of time. It's important to follow the units here. A volt is just an abbreviation for joules per coulomb. That's a volt. Joules per coulomb. Yeah, joules per coulomb. Current, amps, is coulombs per second. If we multiply these two, we get joules per second. If we multiply by time in seconds, we get joules. So that's how we're going to do it. Supply a certain amount of energy that we can calculate, and so know the number, and then measure the temperature change. And we'll be adding that amount of energy to a known mass of water, and then we're good to go. All right, so if we foresee in that mother equation, C above here, right above there, we end up with this, where Q, we're representing Q by this here, and then here's the M, and here's the delta T. Where did this come from? Well, this is actually just a correction, a small correction to the fact that in this case, the styrofoam and other components actually absorb a little energy. All right. Now to the aluminum. How going to do the aluminum? The aluminum is a system. What we're going to do is we're going to put an aluminum in a test tube, then heat it to 100 degrees, some aluminum block. It will know what the mass of that aluminum is, and then we're going to take it and put in our calorimeter with a known amount of water, 40 grams or thereabouts. And this time we'll know the water, we'll know what the specific heat capacity of the water is, and we'll measure the temperature change. So if you look at the equation, Q system plus Q surrounding is equal to water. Both of these are undergoing temperature changes. So C metal, that's what we're looking for. Mass metal, we know this. Delta T, we can determine that. Seawater, at this point we know what seawater is, the 4.184 joules per gram per degree centigrade. We'll know the mass of water in the styrofoam cup, and then the temperature change, and then we can do that. This then is a correction term, correction to the fact that in this case the styrofoam and other components, the step actually consume energy. Good. Ice. I'm going to take ice from the freezer. There's a little freezer outside my office here. So you measure the temperature of the using the data logger, figure out the temperature of the ice in the freezer. So what will happen to the ice is threefold. It will be a certain amount of ice that will then be heated from the initial temperature, sort of minus 14, minus 12 degrees centigrade, or something like that. We're going to bring it to zero. There's a delta T there. Then we're going to go do the enthalpy change. It will be 0 to 0, because we're not at that point causing a temperature change. All the heat energy is going into the melting. And then now we're going to take that same, now it's water, from the ice, from 0 to the final temperature. So here's the expression for the ice from its initial temperature to 0. Will tell you what the specific heat capacity of the ice is. You will know what the mass of the ice is, and then figure out what the delta T is. For the enthalpy, for the melting, call that Q2. Well, we just have the mass and the enthalpy. And then for the water, this is the water that came from the ice. It goes from 0 to its final temperature. So we're going to set up a whole system that says Q system plus Q surrounding is equal to 0. And so it'll be a long expression this time. So let's go. Here's Q1. Here's Q2. Here's Q3. Here is Q surrounding. And here is the correction term. So when we've done the experiment, we'll know everything except that one. It's an equation equal to 0, so we can solve it for enthalpy of fusion. As we solve this equation, very important to keep the signs straight. First, figure out which is the ice and what's happening to the water from the ice. And then think of delta T, final minus initial. Final minus initial. And then the rest is simple arithmetic. Just keep track of how you do it and then it should be good. At the molecular level, what's happening to the energy system? So when we change the temperature, we're increasing the kinetic energy of the system. And so in our case, just to simplify our life, within one phase system, we'll say when we're changing the temperature, we're changing the kinetic energy. But we'll say we're not affecting the potential energy. So if I go from 5 degrees to 95 degrees, and this is water, the change in the potential energy is 0, the change in the kinetic energy is sizable. However, when you get to any phase change, then we'll say the change in the kinetic energy is 0, and the energy we're inputting or collecting out of the system is going to changing the potential energy. So that's our mental view of the energy level system when we do this experiment. Moving right on, specific heat capacity of water. So here it is. Here's the heater head. So here is resistance wire. Okay. And we're going to dip this in a styrofoam cup. There shouldn't be a copper metal here. There shouldn't be anything at all. The only thing that we're going to put in here is a small temperature sensor. Okay. And this is going to go in a styrofoam cup. And then we want to set this appropriately. What does that mean? It means we're going to read from here the voltage and here the current, right? And then from the data logger, we'll record the time, seconds that we've spent heating the system. So we'll have the voltage, the current, and the time. And with that, multiply all three, and we get the joules. So here's the setup. You want to note if there's a copper metal here, just remove it because it disturbs might short circuit the system. Here's a little temperature sensor, and here's a power source, right? And so when we start heating, before we start heating, the temperature is flat, and then after we start heating, the temperature rises linearly. That's when we hit play, we do nothing. Here we start heating, and then the temperature rises until after a while, 70 seconds or whatever, we turn it off, and so the temperature then flattens out. So then in this case, here is our small delta T. This is the time in seconds. Over here is a change in the temperature. So those are the two things we need from the data logger. For the heating of the small aluminum block, we're going to put it in here. In the test, you make sure that this is open, so this is loose up here, so that we're not heating in a closed system. Get the water to boil, let it equilibrate, so 5 minutes, 10 minutes of boiling, and then going to take this and pour it into a styrofoam cup with known amount of water. You've already started measuring the temperature of the water, and then you put that in, and then the temperature of the water will increase. So in this case, for the metal, we started 100 degrees or whatever temperature we measure here. So that's T initial. T final is the final temperature of the water. So watch out for the delta T's and make sure you're thinking through and performing the delta T calculation appropriately. If it gives you a negative number, the negative is important. Heat or fusion of ice, that's an easy one. You set up the data logger system with a known amount of water in here. You start recording the temperature. You go get some ice from the freezer outside my office or thereabouts, and then you measure the temperature of the ice in the freezer. You quickly come and drop and measure the mass of the ice in the freezer. Come and drop it into the styrofoam cup, and then you measure the temperature until it equilibrates, until the ice all melts, and then you have all the data to do all the calculations. All right, so for the first part, of course, when we heat electrically, the temperature will be going up. All right, and then in terms of the second part, the temperature of the water will be going up. So gotta look at whether you're looking at the system or the surrounding. All right, there are the literature values. Yes, so you know whether you're getting anywhere close or not. I might have said this wrong. 333 joules per gram. And here are the sort of values. So as you do the calculations, you'll know that you're in the ballpark or you've made some calculation error somewhere. Safety issues, well, don't burn yourself. Watch out for the temperature sensors so they don't come close to the heating sources. And as you do the experiment, remember you're trying to mix things, so keep stirring it at all times. And yeah, there's nothing dangerous here, but we're still required to wear our goggles as long as we're in the lab. So for this lab, most of the calculations you do in the lab and answer the questions in the lab. So do all that you're supposed to do in the lab before you leave the lab. Great lab, great match with what you do in class. So this is a time to reinforce, clarify the concepts, and also, of course, master the practicalities of it. All right. Thank you. Have a great day.